plate is the one that takes more work. The electric field of a ring. So to do the proof, you just say, okay, take a piece of the ring over there, take a piece of the ring over there, and then say, okay, the electric field created by that piece dq is going to be this way, dE, and then this piece is going to be dE that way. So oftentimes we're using symmetry. So in other words, one piece from the top, one piece from the bottom, and then their x components only survive, dE total, and then this is theta, this is also theta, and their y components cancel. So you could say dE total is equal to 2dE cosine theta. Okay, and then you say 2dE is equal to k dq over r squared cosine theta. And then where r is this distance, right? Then you integrate that for every pair of pieces. Imagine another pair like this, another pair here. So I'm going to try to see if I could draw this 3D. It's like, looks like this. That kind of helps a little bit, right? So you're taking a piece from here up there, then taking a piece from here, and then those two will create an E field like this, like this. And then you're coming down that ring. Eventually you're gonna get to here. That one will create an E field going into the paper. It's hard to draw that like this, kind of, you see. And then another piece from the other side will create a, like this, you see. So it'll be kind of like, the one of them is like this. Imagine two pens like this, up and down, you see. So that one is created by the top piece and the bottom piece. Two E fields like this, equal length, you see. And then their X component survives. Now from the piece here and the back piece, then it's like this. Hold on. This is like this. And then the other one is like that. Let's see, where is this? But the sum of these two is still the same as the sum of these two, you see. So as you're going around the circle like this, you're essentially getting like this, you know, you're going like that. So these two added together give you this, you see, their X components survive, and it gives you something like this. And then if you add these two, you still get something like that. So you're always getting this. It doesn't matter what plane you do. It's almost like a cone here that you're getting. You see, this and that gives you that, this and that. So this and this gives you this. This part of the cone and the other part of the cone gives you this, and so on. So then when you integrate this, actually nothing is integrable. You don't need to integrate anything because it's all constant. The distance is constant, and this is X, and this is R. So then you're just gonna have, everything comes out of the integral, 2k over r squared cosine theta, integral dq. This is q, and this is theta. It's not the same letter. Sometimes it confuses. This is theta, and then this one here is q. So since the theta is constant, and r squared is constant, everything comes out. So then the integral of dq, you integrate over half the ring because you've already accounted for the other half by doubling. So then the integral of dq just becomes q over 2. Q over 2. See, I'm integrating over half the ring. Right? So Q over 2. Okay, then this 2 and this 2 cancels. Okay, this is the electric field of a ring. So K, Q. Okay, how do I write R squared? So R squared is going to be X squared plus R squared. X squared plus R squared. Right? That's already the R squared. And then cosine theta is going to be, this is theta. And it's the same as this theta. You see the theta of the electrical field is the same that the theta that this is making. So cosine theta is just simply X over another R, but this time it's radical that. So X over radical. So we've seen that before where we get a 3/2 power, right? So in this case, nothing, we didn't have to integrate anything because the angle, as long as we're at the center axis of the ring, the angle between any element of the ring and that point is constant, as long as we're at the center, right? And the distance is also constant. Now, it's different if we want to find the electrical field at some random point. That's a much harder question. You know, you have a ring like this and you want to find the electrical field at some random point. That's what that app does. That app is able to give you the electrical field at any point. You play preview. You see, at any point, including the center axis. Oh, there you go. Give it to us. Yeah. You see, so I'm only doing the center axis. Okay. Oh, I'm just looking at the chat. You guys were discussing about that. It's only centered. Yeah, Daniel, good answer. So for every pair, you create a cone of vectors whose sum of the two is always in the x direction. You see, so you're creating a cone. So of course we can't just sample only this and this. We're gonna do this and down here, and we're gonna do this and then up there. So that's why when we integrate this one over half a ring, that already includes that we're integrating it, the whole ring. You see. Okay, so once we get the answer, we can check if the answer makes sense. Okay. Let's finish my. So K, Q, X over X squared plus R squared to the 1.5 power. Okay, I could do a couple things to that to see if it's making sense. First, let me find the electric field right at the center of a ring. We do expect that the electrical field there should be 0, right? Completely, because you're surrounded by charges. So if I put 0 here and 0 here, I should get perfectly 0. Okay, it does check out. So that's one check. Okay, then the other one is take the limit as x goes to infinity to find the behavior of the electrical field. So the ring should start looking like a point charge when you go far away, right? So how do we do that? Okay, when this is very large, this begins to have less and less effect on it. So this disappears, you see? So then you have x squared to the 3/2 power. Okay, and then you have what? KQX over x cubed. Aha, the famous equation, KQ over x squared. Okay, so you see the electrical field of a ring begins to look like a point charge. So you see the electrical field goes like this, like they're showing in that Wolfram map, like that. Except in the middle, there's no electric field. So just like this. But then when you go to infinity, the ring looks like a point charge to you. So as you go very, very far away, it's going to look as if the E field comes out spherical toward you. So it's going to have spherical symmetry. So if I'm very far away from the ring and I find the E field here and I double my distance, the E field should drop as 1/4, 1/4, right? So to say that it has a 1/x squared behavior is always to mean if I double the distance when I'm far away, if I double from any distance, the E field should drop like 1/4, you see? And it has spherical symmetry. So it's checking out. That's good. That's perfect. The other thing we could do is find out the behavior of the E field when you're close to the ring, like right here, but not way at the center of the ring. So limit as x goes to 0 of the E field. Then when this is small, this disappears, and then this survives. R squared to the 3/2 power. Okay, and you get what? It's a linear behavior, but it's actually not a linearly decreasing behavior. It's not a 1/x. So that means actually the E field increases as you go this way, up to some point. Then it reaches a max, then it decreases. I see. So it increases linearly. So it goes KQX over R cubed. So it linearly increases. That means the E field of a ring looks something like this. It starts out at the center of a ring, the E field is 0. It linearly increases, right? The behavior when I'm close to the ring, the E field gets larger actually, up to some point. Then it starts to make a maximum. Then it starts to decrease. And when you go to infinity, then it has a 1/x squared behavior, you see? But near the ring, it's got a x behavior proportional to x. You see? So what does that mean? That means that I kind of drew this field lines wrong. This is what it should look like. A better drawing would be like this. Where's my papers? This makes it look like the E field starts out at some value and then weakens. As the E field diverges, it weakens. So it should be more drawn like this. Let me draw a horizontal version of it. So the E field starts out from the ring, right? Because the ring is what's creating the E field. It goes like this. So this is the center line. So it goes like this. Then it starts diverging out. Okay, you see something like that. So you see what's happening? As I start here, the E field is 0. As I go that way, what's happening to the E field strength? It's getting larger, 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 larger. When does it reach the maximum strength? Right here. You see? Then the field starts to decrease. And as you go very far away, this begins to shrink. And then the lines come out to you like a spherical lines. You see? So this is the point that gives you the maximum E field. So it kind of comes in and then goes out. You see? How would I find that point? The point where it gives you the maximum E field. Let's see here. Take this, take the derivative of this, set it equal to 0. Right? So this is the general equation. E equals KQX over x squared plus r squared to the 3 halves. What would be the derivative of that? I don't need this if I want to just know the point that maximizes it. Those are constants. So I can say dE dx is equal to this times the derivative of that minus this times the derivative of that, the quotient rule, right? Times the derivative of that. So I'm doing this, which is this, times the derivative of that, which is 1, minus this, times the derivative of that, which is you bring down the 3 halves, times 1/2, times the derivative of the inside, which is 2x, over this thing squared. So then you're going to have here x squared plus r squared to the 3 halves, minus the 2 cancels the 2. So then I have 3x squared, x squared plus r squared to the 1/2 over x squared plus r squared to the 3. Then I can factor out the x squared plus r squared to the 1/2, right? And I'm left with what? If I factor out the 1/2, I'm left with just x squared plus r squared. Minus, and then this is gone. So this is 3x squared. So you've done this, I'm sure, in Calc 1, right? Where you use the quotient rule and then you factor out the greatest common factor. Okay, then you will divide it by x squared plus r squared to the 3. Then you're going to set this equal to 0, right? To find the point that maximizes. So right here. So graphically, the E field as a function of x looks like this, right? Straight line, then it starts curving, right? Right here. I want to know what that x is. Okay. So set it equal to 0. So then you're going to have what? X squared minus 3x squared negative 2x squared. Right? Let's see, x squared plus r squared minus 3x squared Okay, so then that's negative 2x squared plus r squared is equal to 0. So then 2x squared is equal to r squared. X is equal to r over root 2. Oh, okay, so whatever the radius of the ring, oh, that means the maximum occurs quite fast, like right around there. Whatever the radius of the ring, even less than radius of the ring over 1.414. So right around there is where the maximum occurs, like this. Something like this, rapidly. It was like this. Of course, it's the same thing on the other side. It's symmetric. Okay, so quite right away, you reach the maximum electrical field. Then it starts to decay. And then when you go out to infinity, it looks like the electrical field of a point charge. Let's see. Okay, now let's do, okay, we're ready to do the plate then. So how do we find the electrical field of a plate? Or let's get a number for that so that we can then later on compare them. So let's say if our ring had a charge of, let's make it the same charge, 10 nanocoulombs. And let's say the radius was the same as the radius of the other semicircle, 0.5 meters. Okay, what would be the electrical field 1 meter away? 1 meter away. Okay, so then we would do, I'll just use this general equation here, right? In this case, since it didn't evolve an integral anyway, there's really nothing to integrate. It's just kqx over this. So 9 times 10 to the 9th times q, which is 10 times 10 to the minus 9, times x would be 1 meter away over 1 squared plus 0.5 squared to the 3/2 power. That's it, basically. Okay. So this would cancel this. So this will just be what? 90 divided by what's 1 squared plus 0.5 squared? 0.25. 1.25 to the power 1.5. 64.4 newtons per coulomb. Okay, it's not that big, 64.4. That's probably be somewhere here on the graph, 1 meter. This is half, like somewhere here. What would be the maximum value of the E field for that ring? So then we know that the maximum value occurs at r over root 2. So 0.5 over root 2. 0.354 meters. You see so here the E field at 0.5 is 64. So I'm assured by doing my derivative that the E field at 0.354 is going to be larger than 64. You see, it's going to be larger than this number. So what is 0.354 squared plus 0.5 squared, close parentheses, raised to the power 1.5. Yep. Way bigger. Wow. 138.57. That's the maximum value of the electrical field. Yeah, you see, imagine 0.354, if that's here, 1 meter is like here. Oh yeah, by that point, the electrical field has diverged quite a bit, and it's a lot weaker. Oh, excellent, excellent, excellent. Okay, now let's do plates. So